Hello, I'm Rich Eisenberg, the editor of Inorganic Chemistry. As part of our 50th anniversary celebration, we are conducting interviews with leaders in our field. Today's guest is Professor Steve Lippard from MIT. Steve is a very distinguished inorganic chemist who has won the ACS Award in Inorganic Chemistry, the ACS Award for Distinguished Service in Inorganic Chemistry, a number of other awards, one of which we're celebrating this year, the Biomimetic Award, named for Ronald Breslow. Steve is a member of the National Academy of Sciences and also a Medal of Science winner. Welcome, Steve. It's a pleasure to have you here.
Pleasure to be here.
Steve, let's begin sort of at the beginning. So tell us a little bit about how your interest developed in science and chemistry and moved you forward to the career that you're on now.
Well, I was a Pittsburgher, grew up in Pittsburgh, and greatly admired an uncle of mine, my Uncle Mo, who was a physician. And I always wanted to be a doctor, and in particular I wanted to be a brain surgeon for some reason. And I was fortunate to be able to go to Haverford College as an undergraduate. And of course, in order to study medicine, you have to take courses in chemistry. And I had wonderful chemistry teachers there, and they really inspired me to get interested in a research career. We also had a visiting program there called the Phillips Visitor Program. And during that period of time, some very distinguished, renowned chemists came and visited and spent a week on the campus interacting with the students. People like Linus Pauling, Melvin Calvin, Carl Djerassi, inventor of the birth control pill, etc. And it was an experience that opened my eyes to the type of exciting life one could have as a research chemist. But in addition, back in those days, there was a tendency for people going to medical school to major in the liberal arts. So I was a pre-med English major up through pretty much the middle to the second semester of my junior year. And I had a very difficult choice: medicine, chemistry, or a graduate career in English literature. And I did everything I could to make the decision rationally. I went and watched a friend of mine's father do an operation of a hernial sac and visited research universities and also thought a lot about English literature. Bottom line is, like all important decisions in life, I learned at that point, are made in the stomach, not in the head. And chemistry just had too strong a pull, so I decided to apply to graduate school and follow a career in chemistry.
Now, you worked at MIT for one of the real giants of our field, Al Cotton. Tell us a little bit about the lab at that time and Al as a young man.
Well, of course, I was pretty naive coming out of Haverford. There weren't a lot of chem majors. There were some. We had a very good chemistry faculty. And the two places that were renowned in chemistry were Harvard and Caltech. So I applied, I got in, I had an NSF fellowship, and during the process of trying to decide which one to go to, I discovered that neither one of them had the area of chemistry that I was particularly interested in the subject of our interview, which is inorganic chemistry. And so I began to look around, and as luck would have it, that year, for the first time, the American Chemical Society initiated and awarded to Al Cotton at MIT the first ACS award in inorganic chemistry. So I thought, well, that has to be the man. And I inquired about him, and he had a reputation for being a rather hard-driving individual, and I think I'll just leave out any of the other negative things that were said about Al in those days, and there was a lot of them. And I just decided, I would go up and see for myself. So I went up, I visited, I spent some time with him. I found him charming, stimulating, and it was love at first sight. Basically, that's where I was going to do my PhD.
Now, in that work, you I think studied rhenium clusters, metal clusters, and I know that metal-metal bonding was a part of that particular time period. And yet, you're best known for your work in bioinorganic chemistry. So how did the transition come about?
Well, the interest in medicine was there. And so as a graduate student, I also audited courses in biology. And I knew that once I launched my independent career, I was going to work at the interface of inorganic chemistry and biology. I think the first person who opened my eyes to that being an important area was one of these Phillips visitors at Haverford College, a man by the name of F.P.O. Dwyer, Frank Dwyer. He was an Australian. In fact, I'd even considered doing a PhD with him in Australia. But unfortunately, he passed away. In fact, his son got ill. He had to go back to Australia. I drove him to the Philadelphia airport, put him on a plane. He went back to Australia. And he himself, unfortunately, passed away shortly thereafter. But he was interested in the use of metal complexes in medicine, which I found fascinating. Here was my interest in inorganic chemistry. Here was my interest in medicine. It just seemed like a logical continuation of both of those interests. So, of course, I didn't choose a bioinorganic chemist to do PhD thesis work with in those days because there were very few of them, actually. And they weren't in the places that were renowned for deep training and graduate work in inorganic chemistry. So I went to MIT, and then when I launched my independent career at Columbia, where I first met you, happily, that's another whole story which we can get into if you want to, I started several projects, some of which were pure inorganic projects, as you may recall, but some were, in fact, the fledgling projects that began my course in bioinorganic chemistry.
When did you first start working, let's say, on the platinum anti-cancer drugs? And I believe it was right about that time that there were the first reports of cisplatinum from the Rosenberg laboratory.
Yeah, that's true. In fact, Rosenberg's first discovery of the interesting effects of cisplatin in E. coli cells was in 1965, which was 1 year. It was the year I got my PhD and the year before I started my independent career. But I found that interesting, but that's not how I started and got interested in platinum. So among the various projects that I started when I began my work at Columbia was to sequence DNA in the electron microscope. So I had heard about that general idea from Bill Phillips at DuPont. DuPont tried to hire me coming out of graduate school as well. And I had some really stimulating interactions with the DuPont people. And Bill pointed out some work that was going on at Johns Hopkins by a biophysicist who had this idea of putting heavy atoms at base-specific sites on DNA, spreading the DNA out in the electron microscope, and using the electron microscope to pick out the heavy spots on the DNA molecule. So his name was Michael Beer, and so I was looking at the way he was doing it, and I thought that I could do it better. So we began this process of substituting the oxygen atoms in the sugar phosphate backbone, the so-called non-bridging oxygen atoms, the ones that are available for metal binding, by sulfur, thereby introducing soft bases in the Lewis, hard soft acid-based theory that was prevalent at the time, putting really basically a true soft ligand in the DNA molecule, which otherwise doesn't have them. There were some RNA molecules that did have sulfur, and we tested our ideas on them. For example, a transfer RNA that contained a 4-thiou, where the sulfur is actually part of the base and not of the phosphate. And it worked like a charm. That is, we could add mercury compounds, platinum compounds, note the word platinum, other heavy atom compounds that would be good for microscopy, but which would also be targeted at these sulfurs. And that worked. And in fact, as an aside, that's how we discovered the intercalators, because when we got around to terpyridine platinum cation, which I know you've worked on,
yep.
And we proved the syntheses and so forth, worked on it back then, it went in to bind that sulfur atom in transfer RNA better than other compounds which were sterically less hindered. And I thought there had to be some sort of additional interaction that was altering the structure of the tRNA stem, which is double-stranded. And I knew about intercalation, and Charles Cantor was a colleague of mine at Columbia at the time, put me in touch with Jim Wong, and Bill Bauer was the graduate student, one of the first graduate students of Jerry Vinograd at Caltech, who discovered superhelical DNA. And one of the ways of determining intercalation is to unwind superhelical DNA. Long story short, that was the work of Karen Jeanette, later Karen Wetterhahn. We did all that work with platinum compounds. So there's platinum nucleic acid chemistry. And then with respect to the sequencing, coming back to that, what we did was I got in touch with a guy named Fritz Eckstein, who invented a very interesting molecule, nucleoside triphosphates, alpha S. In other words, the first phosphate of the three after the, say, adenine, ATP, had a sulfur in place of one of the oxygens, making that phosphorus atom chiral. And his idea was to try to see if he could understand the enzymes that used ATP, whether the R versus the S, or in those days D versus L isomer was more effective. It was perfect for what I wanted to do, because you could take a DNA template or an RNA template, you could take a DNA or RNA polymerase, you could copy the sequence, but in place of one of the nucleoside triphosphates, you put in the nucleoside triphosphate alpha S, which we got from Fritz. So then you could have thousands of nucleotides long, and every cytosine would have a sulfur. And then we could platinate that or mercurate it, lay it out in an electron microscope, and read the sequence. This is long before the chemical sequencing came along for the human genome, right? There wasn't even any discussion of that. So then the question, and it worked. As far as we could tell, it was quantitative, the metallation. Put in, out of 1,000 nucleotides, 250 GTP alpha S's, you get 250 platinum atoms per DNA. So then the question is, could you see them in the electron microscope? And I must have spent probably integrated 6 months of my time out at Stony Brook with a guy who had a scanning transmission electron microscope. And the bottom line is, the energy that you needed to resolve the 7 angstrom separation between those backbone sulfur atoms was just a little bit too much, and the DNA moved, and once it moves, you lose the information. So it was frustrating. We did use those reagents for other things. The tricks were used for other things. We had a lot of nice data. And all during that period of time, which is like 1966 to early 1970s, you know, the platinum drugs kept coming. 1978, they were approved by the FDA. And I thought, at that point in time, I said, you know, and I became more and more fascinated with them. I said, well, I've got to know as much about how metals react with nucleic acid as most people. Let's go in and ask the simple question, how do they work? So we launched a program, in part with Bill Bauer, my colleague at Stony Brook, who I worked with on superhelical unwinding. And then, you know, in my own, by that point I had also spent a sabbatical. I've spent 5 sabbaticals, and the first 2 of them gave me the training in biological sciences that I needed to really convert my lab. First one was in '72 with Bo Malmström in Sweden, taught me enzymology. I worked on cytochrome oxidase, as a matter of fact. Mm-hmm. And then in 1979 I worked with Aaron Klug. That was spectacular, at the MRC lab in Cambridge, with Aaron and Max Perutz and Fred Sanger and Sidney Brenner, and at lunch every day they had this wonderful lunchroom where you could exchange ideas. And so through those 2 sabbaticals I was able to transform most of my lab into, most of the part of my lab that was doing this into doing the biological work, and we took on the platinum problem.
Is that also how you became interested in iron? Because there's a tremendous amount of iron chemistry you've done over the years, and in different directions, but is that where it started?
The original interest in iron was in iron-sulfur clusters, and I was working on that coming right out in 1966, 1967, and I had Dimitri Koukouvanis as a postdoc, and we wanted to figure out the iron-sulfur clusters, what they were, because there was no crystallography. So we did the first biomimetic chemistry in that area. And the question of what this acid labile sulfur was, if you took the proteins like ferredoxins, and you put acid on them, you could smell hydrogen sulfide. So the question is, where did that come from? Of course, it could come from sulfide, which we now know to be true. Back then, there was a very good group at Berkeley that was claiming that that sulfur was part of a persulfide unit, so RSS. And Dmitri had come from a lab where he had done a lot of that work, so we made those compounds. And the compounds that were subsequently, not a few years later, found to be the true analogs by Dick Holmes' group at MIT, we had those in our hands and discarded them because we had the wrong cations. We weren't able to precipitate them out and study them. So that was the first iron work, but the large amount of work that we've done recently really came when I moved to MIT. I had been fascinated by dimetallic sensors, not just the ferredoxins, but I worked for years on superoxide dismutase, copper zinc system. And when we moved to MIT, I had 3 people, a postdoc, Bill Armstrong, and 2 graduate students, Sergio Gorin and Alan Spool, work on 3 different dimetallic sets, and I wanted like 3 fishermen in the ice, 3 holes in the ice, and I wanted to see which one would strike the fish first. And so Bill worked on the diiron systems. He got the first fish. That was the hemerythrin models, now methane monooxygenase. Sergio was working on dicopper of the copper hemocyanin type systems and enzymes. And Alan was working on what I called Scorpio porphyrins. That is, and I invented the name because nothing was working and we wanted to have a name to sort of make people feel better about what they were doing. It was a porphyrin with a tail. And we had the iron in the porphyrin and copper in the tail, just like the cytochrome oxidase, which I had worked on in Boo's lab. And so once Sergio not Sergio, but Bill was successful, I did what I think any good research advisor has to do. You redeploy your resources onto what's working well. So I moved the other 2 fishermen over to the hole where it was working well, the iron system. And to this day, we're still doing both biomimetic and enzymology on the non-hemed iron systems, which I find to be incredibly fascinating, methane monooxygenase and others of that class.
Let me ask, this is perhaps an unfair question, and that is the proudest research accomplishments that you have, because you've had many, or perhaps that particular unique moment or moments that really will always stand out in your mind as nailing a problem or putting you in a direction that you didn't expect to be going?
Okay, well, there are a lot of them. And I thought about this, actually. So I would say probably the first was when Karen, Jeanette, and I were at Princeton with our platinum terpyridine, and we had to block the 4th position, so we replaced the chloride by mercaptoethanol. Right. So it would be non-covalent binding, and we knew that we had an intercalator. We went down and worked with Bob Langridge and his postdoc, Peter Bond. Peter Bond, perfectly good English name, got his PhD under Wilkins, the Nobel Prize winner, who shared with Watson and Crick for fiber diffraction studies of DNA. So we pulled fibers of calf thymus DNA, I believe it was, but standard garden variety DNA, into which we had added a saturating amount of the metallointercalator. Now, there was a theory about intercalation called the neighbor exclusion theory. And that was, if you took one of these flat metallo, and that, I coined that name, metallointercalators. If you take that metallointercalator, put it in between 2 base pairs, the next nearest neighbors would be excluded. So that you would have, at saturation, now of course it was not cooperative, so it would be some distribution. And the distribution was actually worked out by a mathematician, if it's random, in 1950 in the Journal of the Royal Statistical Society, taking a line of points and making vacancies subject to the neighbor exclusion principle. In other words, you make a vacancy, and then you make another vacancy, you make another vacancy, and you just do that until you run out of vacancies. But you can't have 2 adjacent vacancies. Mm-hmm. So that's the neighbor exclusion principle. And it has a closed solution. It's 1 minus e to the minus 2 over 2, which I always found really cool. And so it's about 44%, not 50%. And so we pulled fibers, just like Wilkins did with Peter. We was at Princeton where language was. It was late at night, not at late night, it was a summer afternoon, evening. And we knew what we would be looking for, and then we got the film. And on the film we saw the famous cross pattern of DNA, which is what led Watson and Crick to figure out what it was. But in addition, superimposed on that were meridional reflections at 10.2 angstroms, dark as hell. Because the platinum gave that intercalator much heavier electron density than, say, ethidium or other intercalators, and you could see intercalator, base pair, intercalator, base pair, 3 aromatic thicknesses, 3 times 3.4, 10.2 angstroms. That was one such moment. It was really thrilling. Absolutely thrilling. That was the first one. Another one, also in the platinum area, came with my now very famous graduate student, Jackie Barton. And Jackie, who I was very privileged to have in my lab, was working on intercalators. But in addition, I convinced her it would be interesting to look at something known as the platinum blues. And actually, she wasn't the first student. An earlier student, Elliot Lerner, Yitzhak Lerner, he's now in Israel, began, and we didn't crystallize it, but we sort of figured out what it was, I think, correctly. And the trick was to change the ligand to alpha-pyridone, or 2-hydroxypyridine. So Jackie synthesized, took cis-diamine dichloropplatinum, allowed it to react with alpha-pyridone, and got crystals. So she had these crystals, and they were going to go on the X-ray machine. I think we had a manual diffractometer then or something like that, probably inherited from your days at Columbia. So I went off on a trip, and I came back, and I said, well, of course I was real interested. How did those crystals turn out? She said, they weren't any good. I said, what do you mean they weren't any good? She says, I put them on the Weissenberg camera, or the Precession camera, one of the cameras, and there were no spots on the film. I said, let me see that film. She leans behind, she grabs the film out of a wastebasket she had thrown away in her lab, shows it to me, and I held it up to the spot, and I said, Jackie, you go up to the X-ray lab, change the developer. And 35 minutes later, she came down, there were spots to the edge of the film. Mm-hmm. So we solved it, and it was a truly stunning compound. It was platinum, there were 4 platinums, 3 of them platinum 2 and 1 platinum 3. And so there's a hole in the D shell, and Jackie, very, very talented mathematically, in no time, figured out, using a one-dimensional particle in a box quantum mechanical back-of-the-envelope calculation, that the end-to-end distance between the 2 platinums at the end, if you put it in and looked at the HOMO-LUMO gap, it was 700 nanometers, and the thing was blue because it had an optical band at 680. So that was clearly, and then we published the paper, and then we did a lot of EPR work on Silver, and I got letters from all over the world because this problem was a 100-year-old problem. People, Wilkinson, Chat, all the stars of inorganic chemistry wrote and congratulated me, and it just was nice because to have the knowledge of what it is and just explained all the stuff that was out there. That's what's so fulfilling in science, actually. So that was one of those matters. Another one, which I learned about today, Steve Koch did a very interesting thing when he talked in the symposium for the Breslow Award. And he said his wife, Michelle Millar, was accusing him of not having any hobbies, so he took up 2 hobbies, which was one of them was history of chemistry, and the other was, mathematical analysis from the web or something. Anyway, to make a long story short, he showed some, really interesting. He went to the web and he took my most cited papers and my H-index, which was 105. I don't even know what an H-index is. He explained that, but I don't look at that stuff. And there was a big spike last year, et cetera, And one of the papers that was the most highly cited paper was the one with Bill Armstrong on the work that I got the Breslow Award for in part, which we made the first diiron sensor for hemerythrin. And that was another exciting moment. Another one which was even more highly cited was our very first protein X-ray structure. We'd never done any protein X-ray structures. I had another wonderful graduate student, Amy Rosenzweig, was my student. And I said to Amy, let's try to crystallize this methane monooxygenase protein and see if we can we got it, crystals. I didn't really know what I was getting into. 250,000 molecular weight. The spots were so close together with a 300 and some angstrom axis, 315 or 350. There was no instrument in the Western Hemisphere that could resolve the spots. She had to go off to Japan to scuba to collect data on a massive Weissenberg camera that they had there. But getting that structure, which was a struggle, we had great help from Per Nordland, who I invited to join us. He had done the ribonucleotide reductase. And we got it, and that was a truly triumphant moment, was getting that. There are more, but I can stop at that.
I expect that there are, but I think those are
some examples.
Those are fascinating stories to tell us. Now, you've actually worked with a really large group, or perhaps I should say you've worked with several large subgroups over the years. What advice would you have for a younger scientist who is desirous of following in your footsteps in terms of the science they do? How do you manage to handle that large research enterprise? What special skills are needed? Would you recommend it?
Well, I'm a very organized person. Orderly person. I think I got it from my dad. He would always line up all of the dollar bills that he put away in his wallet facing in the same direction. And I do that, and my brother does that, and my twin sisters do that. And, that's just the way we are. I can't, take it or leave it. That's what we like. And so, I established this subgroup idea sometime during my Columbia days and then on into MIT, and actually a lot of people, including many of my former students, use it now, and many of my colleagues use it. So on Fridays we have subgroup meetings, and there are 5 subgroups right now, but sometimes there were, the first ones I believe started in the mid to late 70s. And Jackie has them, she calls them show and tells. And that's a nice thing to call them, because they not only have to show what they did as well as telling, they have to show the data. That's the really thing. So it gives you and the students a very high respect for data. Right? Data is really what matters. It's where the truth lies. Truth has very long legs. And so if they got to put that data up there, and we're all going to look at, not just me, but the other members of the subgroup, it has to be the best data they can get. And even if they don't understand it, I encourage them to get it up there so that we can talk about it. And that at least helps keep the different areas somewhat apart. But then we have regular group meetings where people will talk about the research, and so it's a good training exercise for the people in the other subgroups to see what's going on. And interestingly, I've seen some graduate students who are pure synthetic chemists ask the most sophisticated questions of the enzymologists or the nucleic acid people during their group meetings, the regular group meetings. So they can, you can learn and be trained that way. So that's part of it. Written reports are very important to me. As a former near English major, I missed it by one course in my senior year. I would have had a true double major. I require my students to write well, and I work really hard with them on that. And they have to write year-end reports. I used to have mid-year reports as well. But year-end reports, they start writing in mid-December. It's due by Christmas. And then I read them all. Right now there's like 1,000 to maybe 1,400 pages overall. And then I meet with each student individually in January for an hour or so and going over what they did last year, and I take notes. And in subgroup I take notes. That is, in subgroup meetings I sit there, I take 5-6 pages handwritten single line notes each subgroup meeting. And I've got many notebooks of this as another way of sort of keeping on track of all this stuff. And sometimes that record is more important than the student's notebook if they don't keep a good notebook. So it's just a matter of getting people to realize that the written record is important, data are important, interpretations come and go. You obviously want to come with a good one. Crystallography, of course, relatively straightforward. You get an answer. A lot of the stuff we do is indirect, whether it's kinetics or spectroscopy or something like that, and it requires a lot of
One of the bottom line on a lot of this is organization and discipline.
Yeah, exactly.
And I think in order to have that, you also have to have the passion for the science, which I think is evident.
Yeah.
Tell me a little bit about how you found...
It has a downside, though, I want to say, for people who might be listening to this.
Okay.
And that is, and I've suffered from the downside. There are times when someone will come up to me, and it might be in a meeting, or it might be, in the hall at MIT, and they want to talk and engage me in conversation. And, I don't do that as well as a lot of other people do. My brother, for example, who is wonderful at it. I have one younger brother and two younger twin sisters. And he's just really good at that. And as a person who's kind of, organized and driven to certain things, that I've always sort of worried that I'm going to miss my next thing that I've planned for myself to do. So, I think if your personality is more of the latter kind, then just go with it. You can't go against your personality. And you might have a little harder time running 5 subgroups.
Okay, let me go back to this question.
You might be a happier individual.
How would you compare the funding situation when you started versus what it is now? What advice would you have for young investigators just beginning their careers with regard to funding and how to frame their science?
Well, for one thing, when I first started at Columbia, we had a license to get grants. The incoming graduate students, many of them had fellowships. So if I had a group of N minus 1 would have a fellowship. Nowadays, just the reverse is true. You have a group of N, and 1 has a fellowship. And so there's a lot less money being given directly to the incoming graduate students than there used to be. And there are some well-known chemists, I believe Roald Hoffman is one of them, who have argued that we should go more back to the other system. It would be helpful. So that being said, I would say that, that's the change between now and then. But there was also a lot less money to go around back then. And you were given a hunting license to go out and get grants, and it was easier to get them, I think, than it is today. One good thing is that young people do have the advantage that most places hiring, let's say, research faculty, and incidentally, if you're a young person and you want to do a career in academics, and that's not the only career that you should have. There's lots of other things you can do. We could talk about that separately. The most important choice is whether you want to work for what's called a PUI, principally undergraduate institution, or a research institution. And that's a huge dichotomy. You got to pick one or the other. I know some people who are actually interviewing at both types, but I would advise against that. You have to really decide which it is you want to do, because they're so different. If you want to, the question you asked, I think, is more directed towards somebody going to a research university, right, who needs to raise funds to run their group. And nowadays, the best, and certainly most research universities appreciate it's expensive for young people to get started, so there's a lot of money that's put into them to get them started, and that can last over a few years. And then I think it's a little hard to break in. I know I've talked to a lot of my own former people who are waiting for that first NSF career award. And when they get it, they're so excited, but you just have to encourage them. Keep trying. If you're getting reports back, listen to those reports and just keep going at it till you get them. And once you begin to break in and get results, things do pretty well. And there are a lot of programs that support young people irrespective of the government granting systems. It's not quite as good in inorganic chemistry as it is in organic chemistry, but it's there. People can get it. It's much harder at mid-career, but then again, we're not talking to the mid-career people particularly in this interview. I don't know.
Well, we can be. I mean, you can certainly provide advice to.
It's harder at mid-career, and I
yeah.
think that NIH has been the main force for funding chemistry in terms of total dollars. The actual reviewing process has changed so that now there is a series of well-defined, well-articulated questions in which for each one, including progress, innovation, things like that, you have to say what the strengths are, but then there's a specific line that asks for weaknesses. Okay? Now, I've long believed that people are judged by their weaknesses, not their strengths. I mean, Shakespeare said it very well. The evil that men do lives long after them. The good is often tarred in their bones. And so the form is specifically asking for weaknesses. Well, I've just gotten some results back on forms, fortunately pretty good ones, but I guess the study sections are learning how to deal with that, and they just leave the weaknesses line blank. There's nothing in there. But the rest of it's sound bites. Instead of a thoughtful paragraph or two or page, you just have a sentence or two, which I think is going to lead to superficial reviews. I feel so strongly about this that I've agreed myself at this advanced stage of my career to be a member of a study section again. I haven't served as a permanent member since the mid-'70s. And assuming that the government approves me, I will join a study section in synthetic chemistry at the end of this year. And so hopefully if there's enough people can come in and try to keep the system working so that the best, most creative things get funded. And it is hard for people who do, say, pure synthetic chemistry without a bio or a materials slant of some kind to make the case. But if it's truly creative work, and that's the key word, if it's a truly creative idea, if you're the first person, this is one of my favorite analogies, to put the footprints on the empty snowfield, there's something, I think, that transcends all applications and has to appeal to the best reviewers. That this is truly creative, this is a new idea. I hadn't thought of this before, it sounds interesting. So I guess I'm an optimist here. I'd like to believe that truly creative work will get funded, even if it isn't going to cure cancer or make a lightweight material that will allow us to do space exploration or convert sunlight to oxygen. And I think the young people coming out should keep in mind that the best reviewers, and the ones hopefully that will be looking at their applications, are going to want to see signs of creativity, which means you don't want to be doing the same thing that someone else is doing, unless you really do have a creative idea about how to do it much better, right? So that would be the advice I would give.
I think that's good advice. Let me turn to the question of inorganic chemistry. That's capital I, capital C, our journal. You've been a valued supporter of inorganic chemistry from the very start. You were an associate editor of inorganic chemistry for several years when bioinorganic chemistry was starting to take off. Tell us a little bit about your perceptions of IC early and in the middle, and how you see the journal progressing going forward.
I would say that the journal has evolved hugely. The field, all of chemistry, has gone from fairly small enterprise to quite a large enterprise in the academic area. And inorganic chemistry has reached out into many, many different areas we have organic, so we have organometallic chemistry. We have bio, so we have bioinorganic chemistry. We have materials, so we have inorganic materials chemistry. And we had materials early, but there's, of course, a renaissance in materials now. It's basically stuff we used to throw away in the 60s is now extremely fashionable. Those of us who are molecular scientists, we get these polymers and get crystal structures, and they were interesting to examine, but nobody thought of them as nanoparticles that might store hydrogen or convert, molecules catalytically and so forth, or carry drugs into people. So I think it's just a natural, it's a natural process of continuation. I think you've done a fantastic job as the editor. And I don't just say that because you're interviewing me. And I think the journal is in really good shape, and there's the associate editors are doing a good job. I was surprised that one of my recent papers is actually being handled by somebody I didn't even know was associate editor, because I don't get the journal and read the masthead anymore. Vivian Yam.
Yeah, right.
And I thought, my goodness, what's Vivian doing with my paper? Which is fine, And I think that's a great move. I mean, chemistry is international. Inorganic chemistry should be international. There's a proliferation of journals worldwide now. The Royal Society, the Journal of the American Chemical Society has discussed this a lot. I mean, there's only a certain amount of chemistry that's being done. And so, it's like jobs in the United States these days, people talking about the jobs. Well, there are only a certain number of people and only a certain number of jobs, and that's the same thing with chemistry in journal space. So if you continue to increase the journal space, obviously each of those, the size of each of those journals is going to go down, and the quality is going to go down, unless it maintains its core, which I think inorganic chemistry has, which I've said this at JAX as well. What we're selling now is not, rapid turnaround or fancy covers or, things to put on the wall. What we're selling is in-depth thinking, creativity, reviewers who are thoughtful and help the authors rather than beat them up, and where everybody cares that the integrity of the scientific system and its knowledge base be improved.
You've been an associate editor for JAX for, is it 20 years?
Longer. I started, I'll tell you, the numerology, I started for IC as the bioinorganic chemistry editor. Was brought on to do that in 1983, just when I came to MIT, or maybe 84. And then I remember being in Germany on sabbatical in Hermann's lab, and I was in this countryside. I think you were there maybe. He had this residence near his residence in Gegenhausen, the little village outside.
Yeah.
And and I got a phone call, and it was Al Bard, and he asked me if I would jump ship, and I felt a little guilty about that. But then I thought, well, then maybe there's just a bigger venue for bioinorganic chemistry, which of course has been my passion. So I did it, and so you can do the numerology. So from 88 to 2010, what is that?
So 22.
22 years, 22
Yeah.
for inorganic JAX, and another 4 or 5 for IC.
So we both look at this question of the future and how students access information today and how different it is from the way they accessed information just 10 to 15 years ago. It's clear that we are going paperless sometime in the not too distant future. I don't know exactly when.
Yeah, it's not going to be this year. We brought that up at that meeting.
But what do you think in terms of prognosticating for scientific journals and the dissemination of scientific knowledge? What are the challenges? What are the opportunities we have?
I think we're going to go more and more digital. And I think the biggest pressure will be the people who want to publish their work without review. And we're already seeing that to some extent, but I think it's going to be much, much stronger in the future. Just like things I don't know anything about but have heard about, like Facebook. I have no idea what that is, but apparently it's putting your stuff out there without review. Or somebody is joining you, asking you to do this, that, or the other. So I think there will be some of that going on, and I think the toughest thing will be to deal with the group of people that comes along. I mean, I look at young kids today, and they're like this, they're constantly going along with their thumbs, texting somebody, and so that once that mentality gets to be in the professorial ranks, then I think to a certain extent it's going to affect how knowledge is disseminated. There probably will be no libraries, it'll all be digital. I think there's no way that journals aren't going to be that way. I don't know if you've seen the new app. Have you seen the new?
I have.
I like it.
You can tell our viewers about it,
yeah, I mean, there's a new. I'm an iPhone person. I love the thing, and I got an email from ACS telling me that I could buy for $2.99 this app, which I have, and it's JAX, right? And I can get the ASAP. I never read any ASAP articles. Actually, I don't read them here either. But the idea that I could read them and immediately, and I might, I'll download them if I'm on the subway coming into work one day. I might just read through and see what, it's kind of a way of browsing and keeping up. So there's going to be a lot. I'm not sure I quite answered your question, but I think there's going to be a lot of technical changes like that will affect what we're doing, and the key is to make sure that it doesn't influence the strong basis on which we stand, which is data, factual, reproducible data.
And the other point that you made, peer review, as editors, peer review is essential. We believe in it. It's bedrock to us. And peer review, if done right, strengthens the science that gets published.
No question.
And I think we both feel that way, and we don't want that. We want that to remain constant as we go forward in time.
Yeah, and of course it's harder and harder to get people to do reviews. And the associate editors have to be energetic, and so there really basically has to be more of them in order to remain energetic in this knowledge-rich world. There's ways of getting reviewers which take time. You have to be able to search through the databases and do it. I don't do as much of it as I should, I think, because I'm pretty good at thinking about, when I get a paper to handle. If I can't think of reviewers in the first microseconds of seeing what the title and abstract are, I know I'm in trouble. So, and then of course, I have a fairly limited, I guess, base. But then I have people I trust that they say, well, I can't do it. They almost always give me somebody, and then I'll check that person out. It's almost always somebody who's qualified. Mm-hmm. And certainly I've published some stuff in inorganic chemistry that's been widely cited by people who are card-carrying biochemists. Because it is possible now with the searching algorithms for people to pick that stuff up, more so than it used to be. But you would basically like it to be in a place where the interested readers would see it, right? And so somebody has to decide, well, would an interested reader look at it there? Or would they miss it?
The future might be very different, where you can search and pick up all of the papers, all the ASAP papers that satisfy certain interest criteria.
Right, so you have the abstracts and the keywords, and it won't matter as much what journal it's in.
Yeah.
That's exactly right.
Yeah. So, well, I would say thank you very much, Steve Lippard. This has been a really informative and enjoyable interview. By the way, I also want to extend congratulations on entering grandfatherhood, something that just happened very recently. And we've been fortunate enough to have this wonderful interview with Steve Lippard, and I hope that our readers will enjoy it. Thank you.
Thank you, Rich.